For today's lesson preview, we're going to use ideas that have been presented in Lesson 1 and Lesson 2 in order to finally determine the arc length formula. So arc length is a distance from A, B on a curve of a continuously differentiable function. You are given data and a graph, and I want you to estimate the arc length from x equals -2 to x equals 2 on this curve. Use concepts and ideas discussed from lessons 1 and 2 in order to accomplish your goal. Arc length is going to allow us to find the distance on curves. Now, if we think about what is actually happening with each one of these curves, if we were to draw the distance from one point to another, and perhaps even draw a triangle to connect these distances, we can see that the hypotenuse of the triangle is going to be equal to the distance from one point to another minus some of that curve. But when we go further out, that little bit of curve is going to be an error. So we're actually going to estimate using these values. So if we think about the change in x and the change in y, we know that we could write that the change in x squared plus that change in y squared is going to be equal to the length of each one of these little pieces squared. So if we now know the length of one little piece, we should be able to take all of these little pieces. Oh, so if we're going to do all of them, let's put there some k's in here. Is this looking familiar yet? So we will have then the length of each one of these little pieces that we could solve for and find. That works for every one of our lengths. And you can see that the error for some of these pieces is going to be smaller than the error for all of them. So we've got delta x. Here's another k value. Let's call this one k plus 2. And this is my delta y, k plus 2. And then that gives us our delta L of k plus 2. After you find each one of your delta L's, we know that the arc length, or what we're calling L in this problem, is going to be approximately equal to each one of your delta L's added together. And once you do that, let's see if you can come up with an answer that is close to 5.1856. And because this is an AP course, we're going to round it to our 3 decimals of 5.186. Show all of your work to complete this problem. So our goal is to explain how calculus is used to develop the definition for arc length and the formulas. We know from our work in the lesson preview that each one of our little lengths that create the arc length, delta x sub k, was equal to the square root of each one of the delta x sub k squared plus our delta y sub k squared. In order to find the total arc length, we took the sum of all of these delta L sub k's and put them together. So addition, repeatedly, we're going to take the sum k equals 1 to n of each one of these functions square roots. So we have delta x sub k squared plus our delta y sub k squared. Now, in order to turn our summation notation into an integral problem, we need the limit as n goes to infinity, so that we're creating an infinite number of slices for the sum k equals 1 to n of our function that we have. But notice in this one, we don't have a delta x or a delta y sitting outside that square root. And that's where algebra comes in. So if we were to multiply, let's say by delta x sub k over delta x sub k. So essentially multiplying by the number 1. And distribute the denominator into our function. Let's see what we get. We will have delta x sub k squared over delta x sub k squared plus delta y sub k squared over delta x sub k squared. And outside of the square root, we now have delta x sub k. So there's our dx if we were to write an integration formula. Let's simplify this some more. So the limit as n goes to infinity, the sum k equals 1 to n can be simplified. We have square root 1 plus our delta y over delta x sub k, and that's going to be squared times delta x sub k. And now, since we have the definition of an integral, this is going to be the integral using your x value. So we'll go from a to b, square root of 1 plus, do you recognize dy dx when you see it? So we have dy dx, quantity squared, dx. Let's talk about the dimensions of this. So that's kind of interesting. As we look at dx, you know, is a length. But we're looking for arc length. Arc length is one-dimensional. Length is one-dimensional. That means that 1 plus dy dx has no dimension. So we have a one-dimensional function when we are finished. Also notice that when we're cutting on the x-axis, we have f prime of x. So that's going to be dy dx is equal to f prime of x. But when we're cutting on the y-axis, we have g prime of y. And g prime of y is the derivative with respect to y. So that will be dx dy when you're working with arc length. Since it's one-dimensional, you can choose to use either formula, whether you're cutting on the x-axis or the y-axis. For our first example, we are looking for the arc length of our function from x equals 1 to x equals 2. So you can see it's a nice curved function, so we're not going to use Pythagorean theorem in order to find it. We're going to find the arc length. So let's write arc length is equal to the integral. You have to decide if you're going to use x's or y's. Since I have x values, I'm going to go from a to b. This is the square root of 1 plus dy dx, quantity squared, and we're going to have dx on the outside, so it'll be dimensionless. We know that y can be rewritten as 1/8 x to the 4th plus our 1/4 x to the negative 2. From here, we figure out our dy. dy dx is going to be equal to 1/2 x to the 3rd minus 1/2 x to the negative 3. Afterwards, we probably want to square it. So we'll have dy dx is going to be squared, and we will also add 1 to it. So 1 plus our dy dx is going to be equal to 1 plus our 1/2 x to the 3rd minus 1 over 2 x to the 3rd. That becomes squared, and then you can simplify it. Rewrite your arc length formula so that we know that the arc length is going to be equal to 1 to 2, square root, substitute what we found from our previous work, and if you simplify it, you get 1/2 x cubed plus 1 over 2x cubed, and that is squared dx. And once you simplify that a little bit more, you can find the actual arc length. Remember to round your answer to 3 decimals. For example 2, we want to set up an integral for the length of an arc of your hyperbola xy equals 1, going from 1/1 to 2/1/2. First, we're going to use trapezoids. Then we're going to use our calculator to find the arc length in thousandths place. And I want the thousandths place because that's our AP standard. Again, draw a picture before you begin. So we know that xy is equal to 1. I have a nice little function. Here we go. We're going to go from 1/1 all the way to 2/1/2. So we know what length we're looking for. So if we set up our integral, we're going to have the integral from a to b. I'm choosing to use x values, so I'm going to go from 1 to 2, and then we will have the square root of 1 plus, I need my derivative, so y is equal to 1 over x, or x to the negative 1. So dy dx is going to be negative 1, x to the negative 2. Simplify that and square it. We will have 1 over x to the 4th and dx. All right, so we're going to use first 5 trapezoids to estimate this arc length. Now, if we're using trapezoids, I wanted to remind you that we are going to set the function f of x equal to the square root of 1 plus 1 over x to the 4th in order to find each of these trapezoids. We're going to use our delta x is 2 minus 1 divided by the number of trapezoids, which is 5. Now in this problem, all your delta x's are the same size, so we can work out the delta x in such a manner. If they're different sizes, that causes another problem. So now we have our delta x. The area of our integral is going to be approximately equal to 1/2 your delta x, which is 1 over 5, multiplied by, and you had a nice little formula, as you'll recall, and it starts with whatever your function is. In this case, f, it was defined, so we can use f of, at the first value is 1, plus, and then it's 2 times f at our next value incremented by delta x. So that'll be 1 plus 1/5 plus 2 times f at 1 plus 2/5 plus 2 times f at 1 plus 3/5 plus 2 times f at 1 plus 4/5. And then our last part is just going to be the endpoint, f at 2. So once we've written the formula after that, you can determine the value using your calculator. Now this is an estimate. Next, we're going to use our graphing calculator in order to find the exact area rounded to the thousandths place. You'll write that the integral from 1 to 2 for the square root of 1 plus 1 over x to the 4th dx is equal to 1.132. Now, hopefully your estimate was really close. And if we are looking at the question of whether it's an overestimate or an underestimate. All right, so since our original curve is concave up, and our line segments are being drawn above the curve, then we know that our estimate is an overestimate. For our last example, we're writing an arc length function. Now our y values are greater than 1, and we know that we have the curve x, and we're going to use 1, 1 as our starting point. So we're writing a function to represent the arc length of our curve. The arc length in this problem should be written with respect to y because our function is with respect to y. So we're going to have the integral from 1 to some y value. Then we'll have the square root of our 1 plus some g prime. Notice I'm going to use t in this problem because y is being used as an endpoint. So it's g prime of t squared, and then we'll put dt on the outside. So we have to find g prime of t, which is going to begin as a function of g of y. So g of y is equal to y squared minus your 1/8 natural log of y. We need our derivative. G prime of y is going to be 2y 1 over 8y minus 1 over 8y. Square that and add 1. And when we square it and add 1, we're going to get 1 plus g prime of y squared is equal to 1 plus 4y squared, once you multiply it out, minus 1/2 plus 1 over 64 y to the second power. Clean this up a bit more, add like terms, And you will end up with 2y plus 1 over 8y quantity squared. So then the arc length with respect to y is going to be equal to the integral from 1 to y square root. Remember, we've already simplified, and we're going to substitute the t in. So we've got the square root of 2t plus 1 over 8t quantity squared dt. Simplify a little bit more, and we have our function is going to be equal to the integral from 1 to y, 2t minus 1 over 8t, and then dt. Once we integrate this problem, and we get t squared plus 1/8 natural log, don't forget the absolute value of t, and plus some sort of c. But wait, we don't have a plus c because we are integrating from 1 to y. Substitute your y value in and your 1 in, and you will be set. So you will have y squared plus 1/8 natural log of y minus 1, and we take off the absolute value because your y values are defined as positive values. Practice finding arc length through the lesson follow-up.